Hello, I believe this is live, so it's good, but I think it's okay. I'm just gonna wait for I think it's like on delay. Anyway, I've arranged the questions a little bit differently than what you saw because I think I can go in order better this way, so that's what I'm gonna start with. I'm gonna start with reduction potentials and what voltage is. So I got my textbook. I don't have Hans' voltage potentials, but I do have the textbooks one, and that's what I'm gonna go with. And that's in chapter 20. On 712 is following along. Okay, I got my calculator, so it should be good. I got my iPad to see if my video is working. It should be working, so I'm just going to assume that it is. All right, voltage and calculating cell. What exactly is reduction potentials and how does it work in batteries? Uh-oh. My video didn't work. I hope yours is working. What exactly is reduction to batteries? Reduction potential is basically the idea, it's working, that reduction potentials tell us how likely it is to be reduced. Like if you look at the chart, reduction potential is a negative value. That means you have to input that much to make that happen. So like the top on my list, I'm on page 712 again. Top of my list is lithium, and it has a -3 electron, -3 voltage. That means if you wanted the lithium ion to gain electrons, you would have to input 3 volts of energy, because lithium doesn't want to gain electrons at all. It would rather give up its electrons because it has a low electronegativity, so it hates electrons, so it wants to give them up. So it's a negative value. Well, if you look at something that's positive, like looking at fluorine is the very bottom of my list, it has a positive 2.9 volts. That means it really, really loves electrons. It wants to gain electrons. And I know that because it will produce 2.9 volts of energy to, if I made that happen. So the more positive it is, the more it likes to be reduced. The more negative it is, the more it likes to be oxidized, because you're forcing it to do something it doesn't want to do. So reduction potentials are basically telling us how much energy you need to input or how much energy you'll gain if you happen to make it do what it says it wants to do in those reduction potentials. And the question also says, how does it work in batteries? Not exactly sure what you mean by that, but we use reduction potentials to calculate how much voltage the battery could make. Maybe part B will help you. Can you define what voltage is? Remember you saying some potential difference, but not quite getting it. Okay, so voltage is technically the potential difference between the two electrodes. But what voltage really means, like in my word, would be it's this force, like how much energy can you get out of it? So if you have something that's worth 4 volts, you can get 4 volts out of it. That means that it's a lot more force of electrons going across than 2 volts. For example, if on one side you have zinc and one side you have copper, the zinc hates electrons and the copper loves electrons. So the zinc forces the electrons to the copper side. He hates them, he gives them up. Copper's like, I love them, he pulls them in. This idea of how much you hate and how much you love, how much you force it away and how much you force it downward and pull it in, that force of movement from one side to the other is what voltage is. The higher the voltage, the more you have somebody that hates and somebody that loves. The lower the voltage, that means that you kind of hate it and you kind of love it. So it's how much force you push to the other side. Now, it's not always about how much you love and hate. It can also be about, if you know Shatler's principle, is you're heavy on this side of the reaction, you shift it that way, or heavy on this side, you shift it that way. Same idea here. If you're heavy on this side, that means you're going to want to force your electrons away from you, right, to the other side. That kind of idea. I don't want to give too much there. That might help you on your battery. Okay, so if you remember, voltage is this force of loving and hating and how much force pushes the electrons across. It's not about the number of electrons. It's about the force of the pushing. Okay, the objective says I can use standard reduction potentials to calculate the standard cell potentials. I'm actually going to do this for my zinc copper battery down here. Boop, right here. All right. What does a double replacement reaction have to do with redox? Quick answer is nothing, because it's not a redox reaction. And why is a double replacement reaction not a redox reaction? Let me help you with that. I have, right now I think you're seeing me. Let me show you my screen. Here we go. Okay. Okay. All right. Okay. So we have 5 types of reactions: synthesis, decomposition, combustion, single replacement, and double replacement. Each of these are redox reactions, and redox reactions is kind of a simplified version of reduction oxidation. And a reduction oxidation has to do with losing electrons and gaining electrons, so that means you are transferring electrons. So if you transfer electrons, that means you have to be one of these first 4 types of reactions. Now, a double replacement does not transfer electrons. It is kind of like transferring ions. So if you think about a really simple double replacement reaction, would be an acid-base reaction. Here's my base, NaOH, and my acid, HCl. And when you do a double switcheroo, I'm going to put in some ion charges to make your life easier, hopefully. Na is now going to hook up with a negative ion to make NaCl. And H is going to hook up with the OH ion to make HOH, or water. Now you can see the only thing that's happening here, because there's still +1, -1, +1, -1. All the charges are the same, which means that we didn't transfer electrons. Charges have to change. Oxidation numbers technically have to change. And since we didn't actually change any ions, ion charges being the same as oxidation charges in this case, we didn't actually transfer electrons. Reactions happen because of a driving force. These first 4 types of reaction have the driving force of transferring electrons. That means that's their benefit. That's what they get out of it. Like in a synthesis reaction, we looked at that before. Somebody gives up electrons because he hates them. Somebody takes in electrons because he loves them, and they make a compound because they got to do what they want to do. They got to transfer the electrons. That happens in each of these cases. The benefit to the reaction is transferring electrons, because then everyone gets electrons who loves them, and everyone who hates them gets rid of them. While in a double replacement reaction, the driving force isn't transferring electrons. The driving force is making something. In this case, we're making a molecular compound, water, and it's a liquid. Or another thing we can make is a solid or a gas. In a double replacement reaction, you've got to make a liquid, a solid, or a gas. And that's the driving force. You're making something new. And if you remember that we drew that ionic equation, so we draw what it looks like. So we would draw HOH as H2O stuck together. You would draw NaCl as Na plus Cl minus, separate. In a double replacement reaction, you go from all separate ions, aqueous and aqueous, to something that sticks together. And this sticking together is the driving force for this reaction. So that's kind of a long-winded answer to your question. Your question is double replacement reactions, why aren't they redox? Simple answer, they don't transfer electrons. They switch partners, but they don't transfer electrons. Okay. Let's see what else we got. Okay, we're going to do zinc copper battery. Question is, if a zinc and copper cell is created, what happens to the mass of the zinc? What happens to the mass of the zinc electrode and why? Okay. So these next questions, I'm going to kind of do them all You can see there's 4 I put underneath the zinc copper battery because I kind of do it all in that drawing. Let me get a new piece of paper to color on. And then I'll show you my screen. There we go. Okay. So the zinc copper battery is what I'm trying to show. Yes. Okay. Well, those are terrible buckets. We'll go with it. Yep. So here's zinc. Here's copper. We're going to connect them with a wire. Of course, we need a salt bridge. This is one heck of a rainbow salt bridge if I've ever seen one, but there you go. The most common way to do this is to put zinc inside a zinc ion solution. I'm choosing to put it in zinc chloride. You can see I have zinc 2+, because that's its charge, separate from the chlorines, because zinc chloride is a aqueous or soluble compound. On the other side, I'll put copper chloride. Copper chloride is also an aqueous compound, so I'll put that in there. If I take a look at my activity series, I can see that zinc is above on the activity series. Activity series I find to be the easiest because there's less to look at. But you could also look at your reduction potentials. You would find that zinc has a more positive reduction potential than copper, which means zinc likes to be oxidized. It likes to lose its electrons. So this is the side that loses the electrons, my zinc side. So my copper is going to be reduced or gain electrons. So my electrons are going to travel along the wire towards my copper. Over on this side, my copper side, if I look at my copper side, somebody's got to gain electrons. I've got a couple options. Copper could gain electrons, copper 2+ could gain electrons, or chlorine ions could gain electrons. My normal brain is telling me if I was a negative electron, I'd want to hook up with somebody positive. And that's exactly what he does. Here's my copper 2+. The electrons come to the bottom of this bar and they hang out right here, and copper 2+ is like, yeah, I would like to be with those electrons. So now they connect, and copper 2+ will hook up with these 2 electrons to create a copper solid. The 2+ and the 2 negative electrons balances out to be a copper with no charge and a 0 oxidation state, which is a solid. So we've created more solid. I've taken some of this aqueous stuff and stuck it onto, and it like coats onto the bottom of the bar to make more copper solid. In this way, we can see the electrode, that's the solid piece, is getting bigger. And I believe that was the question, if I remember right. Yes. Oh, we were talking about zinc. Let me go back. Okay, so the copper is gaining, so that gets bigger. But if you look at this, the zinc side, I'm hanging out on the zinc side now. My zinc is losing electrons. And who's going to lose electrons? Well, my zinc 2+ isn't going to lose electrons. He's already lost 2 to become 2+. He wouldn't lose more. My zinc solid becomes the one who loses electrons. So my zinc will lose electrons, 2 in fact, to become the zinc 2+. So every time 2 electrons are lost from this zinc, we create a zinc ion. That's an aqueous thing. I'm making aqueous thing, and I'm losing solid stuff. So this zinc bar gets smaller because I'm losing it and creating aqueous parts. The battery is going to run out whenever I run out of zinc, or if I happen to run out of copper solution. Okay, next question. Can you explain the electron movement in the battery diagram? Starts from here and goes to there. I believe I did that. Okay. As you can see in my picture, the electrons go from the zinc side to the copper side. And they stop here. The electrons hang out at the bottom of the bar, copper hooks on, and the electrons stop right here. So electrons start at the zinc, travel along the wire, and then they stop down here when they've hooked up with copper. How to do this? Can you use standard reduction potentials to calculate the cell? Okay, I'm going to calculate the E cell now. For the E cell, I'm going to take the cathode, or the reduced part, minus the anode every single time. So in my picture here, my zinc side is oxidized, so it's the anode. My copper side is gaining electrons, it's reduced, that means it's the cathode. So I'm going to look up my numbers on my textbook, page 712, at the standard reduction potentials. I'm using the textbook, so it's not maybe the same as Hans, but you could use hers too. I'm going to look up copper 2+. I see it on the sheet is a 0.3419. You probably might have different numbers if you're looking at Han's sheet, but at least the first two sig figs should be the same. That's a 3, 4. Whoa. If I look for zinc, he's a negative 0.76. I just lost it. 0.7618. Okay. So to calculate the E cell, which is how much voltage this battery will make, I'll take my cathode number, boom, 0.3419, minus my anode number, that's my zinc side, negative 0.7618. Bust out my trusty calculator here. And I get 1.1037 volts. Sig fig wise, all these numbers are infinite sig figs that come from the textbook. I can't grade you on sig figs here, so that's about the end. There you go. I think that was all the questions on here. Let me see what oh, we have the last one. How to do full reaction with spectator ions. Okay. Okay, so if we go back to my picture here, my full reaction, I'll do that one in red, hopefully. Come on. Okay, so my full reaction is going to basically take this equation here and add it up to this equation here. So when I add it up, I can see that there's 2 electrons on the right side and 2 electrons on the left side. They cancel out. So I'm really just left with the rest of them. Zinc, solid, plus copper 2 plus, those are the 2 things on the right, aqueous, makes zinc 2 plus, which is aqueous, plus, I'm sorry, this is terrible aqueous writing, but hopefully you can get it, solid. Okay, so those are when I add up the 2 reactions. Now I need to add in my spectator ions, those are the things hanging out. Some of your batteries have different things in different buckets, so adding in spectator ions will be kind of tricky, but you can see that in mine, I've got chlorine ions that are hanging out. So my spectator ions are chlorine ions each time. These chlorine ions are going to go hang out with the aqueous stuff. So I've got Zn plus Cu Cl2 aqueous makes zinc ZnCl2 aqueous plus copper solid. So basically I'm going to take those things that are left in the bucket that don't really do anything, but you needed them in order to dissolve the copper in and dissolve the zinc in, and I stuck them on. There you go. Like I said, it might be tricky when you do your actual battery that we were analyzing today in class, but you know, hopefully you can figure something else. I'll have to be maybe a little lenient on that one. Okay. Last one is how to do oxidation numbers is our last question. Let me get a new screen. Okay. All right. How to do oxidation numbers. I think Han taught this differently than I would teach it, but I think I can remember what she did. She kind of taught you by rules. And so oxidation numbers kind of follow a certain thing, like H is always +1, O is always a -2. If you have an alkali metal, that's the first column, they're always a +1. If you have an alkaline earth metal, those are the column 2, they're a +2. And all the rest, oh, and anything element by itself is worth a 0. When I say worth a 0, it means the oxidation number, oxidation state is 0. Okay, so all the rest you kind of have to figure out. Like if you have NaCl, or maybe we'll do HCrO4, that's H2. Yep, that's the chromic acid. Maybe a little KClO3, and maybe NO2. Okay, let's go with that. Okay, there are my compounds.
We'll consider the oxidation number. We'll start in the top left. Oh, we'll do one more. Maybe an Mg and a N2. Okay. Okay, top left, we'll start with NaCl. Na is an alkali metal. It has a +1. Now, oxidation numbers, this whole thing has to add up to 0. So Na plus Cl has to add up to 0. In order to do that, Cl has to have an oxidation number of -1. So +1 and -1. Taking a look going to the right, H2CrO4. H is always a +1. +1. O is always a -2. That's my rule number 2. And now I got to add things up. So I've got 1 and 2. So I have 2 hydrogens, each worth a +1. That's a total of a +2 right here. I have 4 oxygens, each is worth a -2. That's a -8 sign. So all of this has to add up to 0. In order to make that happen, my chromium has to be worth a +6. +6, +2, -8 adds up to 0. To the next one, KClO3. K is an alkali, +1. O is a -2, always. So now if I add them up, K being a +1, oh, there's 3 of them, so that makes a -6 right here. They have to add up to 0. So I have to ask myself, +1, -6, what adds up to 0? It's got to be a +5 for chlorine. Moving over to NO2, oxygen is always worth a -2. And there happens to be 2 of them. 2 times 2 makes a -4. If it has to add up to 0, my nitrogen's got to be worth a +4. Now if this, let's change it up, happened to be N2O2, it has to add up, that has to be a +4. That means my N would be each worth a +2. My last row here, my magnesium, he's all alone, element all alone. He's worth a 0. He hasn't lost electrons, he hasn't gained electrons, he's just neutral. So oxidation numbers basically tell us where electrons are located. N2, it's only one type of element. Each N there is worth a 0. Hopefully that helps. I think that's all my questions. There we go. I'll give you a minute in case you come up with a question that you want to type in. Otherwise, oh, good. There we go. Questions coming in. I'm going to put my times in red. I didn't do stellar on the times, but at least it was something. Oh, you're welcome to whoever's watching. It's so funny that, oh, bye-bye, everyone. That I can't tell who you are, but you're welcome. Alrighty. I'm going to check my email real quick and make sure I didn't get an email question from you lovely folks. If you need more help with voltaic cells, I do have me drawing a voltaic cell video that's on my website if you need that. Otherwise, it looks like you must be good. I think I'll do stellar tomorrow. If you did textbook homework and you felt like it was easy, that's a great sign. I think a lot of the test is like those ones, and then there's a few you got to think about because I got to do that. But I think you'll be okay. All right.